Please,
Yeah.
Rastko.
Thanks so much, Roberto. Good morning. Thanks for sticking up to the very end. So yes, I'm Rastko Sknepnek. So the title is Numerical Approaches to Curvature, but it's mainly going to be mathematics on the board, right, in the tradition of this institution. I mean, we should use all of this space. And then towards the end, maybe like 15, 20 minutes at the end, I'm just going to tell you how we do numerics and on these objects. And I'm going to tie it to what I was telling you about during the vertex model, because ultimately we are going to use very similar or the same data structure to represent this data, right? I don't need to convince you that the curvature is ubiquitous, especially in biology. All you need to do is look in the mirror, right? And you're going to see, flat, right? Curvature is everywhere, right? From subcellular to cellular to tissue organ, to the big structures. So there was yesterday quite a bit of discussion of the red blood cells. So this is a healthy red blood cells electron micrograph. I'm showing this in the browser because I was Googling these things and I'm not sure about the copyright issues of these images. So I'm assuming that I'm not infringing anybody's copyright if I just show them in the browser, right? That's why I didn't want to put them in kind of PowerPoint. So roughly 2 micron scale. So these are these kind of, how they're called, the concave discs, right? And they have the shape so they can very nicely move through the capillaries. Let's see a few other examples. This is some beautiful textbook. So cell membrane, this is of course artistic rendering. Cell membrane is a lipid bilayer, several hundred types of lipids that are interspersed with the transmembrane proteins, membrane proteins, cholesterol, all sorts of sugars on the surface. There is a cytoskeleton underneath, so a membrane-like structure. If you go inside of the cells, right, so this is again artistic rendering, you have something called Golgi apparatus, which is in here, which is also kind of these very so-called cisterns, very interesting membranous curved structures. You have a mitochondria, which contain 2 membrane, inner and outer membrane. These are responsible for the energy production in your cell. Also very interesting curved structures, right? So curvature is really something which is all over the place. It's not limited to biology. Architects love it. The roof of JFK, John Fitzgerald Kennedy Airport in New York City, right? Probably should undergo renovation. This is somewhere in Poland, so opera, right? So these are at the ages of meters, and this is infamous British Museum, right? So the roof of the British Museum. So what is? I'm now gonna switch off the. So can we switch off the screen? Yeah, and then I go up with this. So what is unique about membranous structures is that they are quasi two-dimensional, right? So we have something I'm going to call this thickness H, and then I'm going to call this L, the lateral dimension of this object, right? And then I'm going to say that in the absolute value, okay, meaning I don't need absolute value because these are all lengths, it's much less than 1, right? So it's much thinner than it's big, right? And in the case of cell membranes, this can be a few nanometers, so 5, 6, 10 nanometers in thickness versus a micron size. In the case of a roof, that can be maybe 10, 15 centimeters versus 20, 30 meters in size, right? But this is the important assumption, is that the thickness is much smaller than the size, the lateral size of the membrane, right? And then you've probably seen a sheet of paper. Of course, everybody did. So what is interesting, if you have a structure like this, it does this, right? Yes, okay, so I'm showing you something which you know at the age of 3, right? The membranes are easy to bend, right? So they can bend, and bending introduces curvature, right? And today we are going to talk about curvature, because curvature was mentioned yesterday quite a bit, but curvature is a rather nasty beast, right? So we are going to discuss essentially what is the curvature, where it comes from, and so on and so on. Right? So the underlying assumption is that physics of these type of objects is going to be dominated by curvature, but changes of curvature, right? So that's the idea, and that's what we want to do, right? So in order to do this, I have to walk a little bit into the differential geometry, right? Now I am going to take the 19th century approach of differential geometry, right? I'm not going to use the modern approach, which is very abstract, beautiful, but convoluted as hell. Right? So what I'm going to assume, that I have embedded 2-dimensional surfaces in a 3-dimensional flat space, and it's going to become clear in a second what I mean. So I'm going to start with R3. Everybody knows what R3 is, right? So the 3 times Cartesian product of the real line, right? I'm going to equip it with a standard topology, which is just a fancy word for saying that I'm going to be able to take derivatives. I mean, I'm going to be able to introduce the notion of continuity, and therefore do the derivatives. And for good measure, I'm going to equip it with a scalar product, inner product, right? So dot product. Now, this is all, we all know this from elementary school, or maybe like, I don't know, junior high school. So this is going to allow me to calculate distances and angles. And in the case of R3, this is all completely trivial, and I'm essentially now trying to be overly pedantic and convoluted for something which is completely obvious. But things are going to become a little bit less obvious when I start talking about the surfaces, right? So what I'm going to do, let me first draw a picture, and then I'm going to be a little bit more formal. Sometimes we physicists like to put arrows in here, although we shouldn't, right? And then let's call this X, Y, and Z, right? And then let me have something like a sheet which lives in this 3-dimensional space, right? So this, some kind of sheet. So how do I describe this sheet? Well, I'm going to describe it. So every point on this sheet, let's call it P, is going to be given by a radius vector R, right? So to be a bit more formal, so let's start. So let's say D is some subset of R2, right? So it's a region in the plane, right? Let's say this plane, doesn't have to be, such that D is simply connected So simply connected means, formally means that the homotopy group of the thing is trivial. In a plain language, it means there are no holes, right? So it's just some kind of blob in R2, right? And bounded. Right? Bounded means that I can put it in a rectangle. Okay? So then I'm gonna also define a function I'm gonna call R vector, right? Which is gonna take points from that domain and map them into R3. This is just a fancy way of saying that I have a function which is a function of two variables u and v, right? Where u and v are elements of this domain V, right? Which in terms of components can be written as x of u and v, y of u and v, and z of u and v, right? So all I've done is I, in a slightly more formal way, wrote this vector in here, right? So I'm taking values from some domain D, and then I am following the position of the, so the end of this vector is kind of drawing me the surface in R3, right? Now, of course, you can start screaming at me if you are very mathematically inclined, because there are way too many functions, and this is way too smooth. So what I'm gonna be a physicist, so I'm gonna assume that all of these things are differentiable with respect to u and v sufficient number of times, right? There are no weird King's self-intersections and stuff like that. So I'm gonna, from a physics point of view, I'm just gonna say this is all well-behaved, whatever that means, right? So that I can actually represent it this way, right? You've already seen this many times in regular classes, right? So for example, I can have u is equal to x, and I can say v is equal to y, let's say, and then I can define a surface of x and y, which is, let's say, x, y, x squared plus y squared, right? So this will be a paraboloid. And so just kind of a parabola, and then you rotate it. And I'm, of course, shooting myself in the foot because paraboloid I doesn't have to be bounded, right? But fine. Right? That would be a paraboloid. Paraboloid, right? I can also write something like this. R of theta and phi, for example. So how does this go? This goes sine theta, no, sine phi. I'm gonna get a sphere. That's what I wanna go with this. Okay, and down here is gonna be cosine theta. So I have to have sine theta, sine phi, and then I have a cosine phi, sine theta, right? So this would be an example of a unit sphere, right? So this is S2, so unit sphere. So this is a parameterization of a unit sphere, and so on and so forth. Okay, so that's the idea. So the idea is that we construct a surface like this, and as you can see, the representation of the surface is usually nonlinear, right? Meaning, so these are nonlinear functions. Okay, so what I want to do now, I want to be able to work with these surfaces. So I want to work I want to essentially be able to measure things on those surfaces. So in order to do this, I'm going to push this up, move this one down. So I am going to define vectors, right? So I'm going to define tangent vectors. So essentially what I want to do is so for my surface, at every point, I want to be able to define vectors that are tangent to the surface. What this precisely means is not completely trivial, but it's intuitive, because if you want to formally define it, you need to introduce curves, and then you need to introduce derivatives to the curves, and so on and so on. But the intuitive picture, sorry, I'm using this as props. So the intuitive picture is that I want to glue a plane, although this plane is too, sorry. I want to glue a plane to every point of the surface, right? That's the idea. Yours? Yeah, okay, thank you. Okay, so that's what I want to do. So I want to define these two vectors, and then these two vectors, as you already can see, they're going to be moving along the surface, right? And that's already a tricky part, right? Because in our elementary school mathematics in R3, we are used that you can move things as you please without worrying too much. In here, things become a little bit trickier. So I am going to define a vector EU, right? which is just going to be the derivative, partial derivative of u, of r with respect to u, which is nothing but dx du, dy du, and dz du, right in here. And that's calculated at a given point P, right? So this guy is calculated at the point P, right? Point P. Right? So if written this way, this is effectively a vector in 3 dimensions, which is somehow glued to this surface. And that's where things, if you want to do it formally, that's where things become tricky, because these surfaces normally don't have to live in any embedding space, but let's not go into that. Right? And then I can completely, by complete analogy, define a vector with respect to v, right? And that gives me the other vector. Same definition. So in general, EU, so these two guys are not orthogonal to each other. In general, they can be, but in general, they're not orthogonal to each other. Right? Also, in general, du is not equal to 1. So they're not normalized. They can be whatever you want them to be, right? However, we are going to require, right? So this is going to be requirement. This is also not guaranteed, but we are only going to consider surfaces where EU and EV, so this pair, is a basis in R2, which is just a fancy way of saying that they are linearly independent, right? So I cannot have a situation where EU and EV are collinear, right? Because then my surface would be wacky. So I'm assuming that everywhere they do whatever they want, but they are never collinear, right? That's the assumption. Okay? Okay, so far so good. Any questions so far? So let me now let me just make the notation a little bit more convoluted but more powerful. So this is a pain to use U and V. So I am now going to use the notation where I'm just going to say that U is, I'm going to call it U1. This is not U to the power of 1. This is just an upper index, right? And then I'm going to say, or this is, I'm just introducing the change of variables, right? U2, right? So the upper index. So which now allows me to introduce a Greek index, which is going to be either 1 or 2, right? So I'm going to reserve Greek indices to be 1 or 2, to be on the surface, and I'm going to reserve Latin indices to be 1, 2, and 3, to be the ones of the embedding space. And now, what I can do, I can write E alpha with the lower index in here is dr du alpha, right? And the upper index in the denominator means the lower index on the quantity. That's convention. This now allows me to do all sorts of interesting things, because now I can introduce the notion of the metric, right, and be able to calculate distances on surfaces. So I can introduce something which is called a metric tensor. I hope everybody knows what the tensor is. In this particular, this is going to be a rank 2 tensor, 2 times covariant in the old notion of covariance and contravariance. So I have 2 lower indices. So I'm going to introduce a tensor, right, with the following components. So 2 indices, 2 lower indices, These indices are 1 and 2, so these are 4 numbers, which is just going to be E alpha dot E beta, right? So if I write it as a matrix, it's not really a matrix because I don't transform as a matrix, but I can write it as a matrix, right? So in here is going to be GUU, right? So this is going to be EU dot EU. This is going to be the EU dot EV, right? This is going to be EV dot EU, and this is going to be EV dot EV. And I'm already violating my convention, right? So if you want to calculate what this is actually straightforward because this dot in here is just your regular dot in the 3-dimensional space, right? So your regular scalar product between 2 vectors. So you take the x component the first vector multiplied with the x component second vector, y component plus z component, right? So if you want to calculate what this is, well, you just go up there, you calculate what EU and EV are, right? And then you calculate dot products and you're going to get the matrix. Okay? So I can also now introduce an inverse tensor of this, right? Which is going to have 2 upper indices. Right? So this thing is the inverse of this. So this is the of G, right? Tensor G. And how is this defined? Well, I'm just going to write it and then we can discuss it. So alpha gamma G gamma beta is delta alpha beta. Okay, so now we have a little bit of a mess. So what I've introduced in here, I've introduced what is called the Einstein summation convention. So whenever you see a pair of repeated indices that one appears up, the other appears down, then you are summing over this, right? So this effectively in here means sum over gamma goes from 1 to 2 of G alpha gamma, G gamma beta, right? That's what it means. So G alpha 1, G1 beta plus G alpha 2, G1 beta, and so on, right? And this in here is the Kronecker delta symbol. So Kronecker delta symbol just means that this is 1 if alpha is equal to beta, and 0 is alpha is not equal to beta, right? So in that sense, this allows me to define the inverse of a metric tensor. So why do I need the metric tensor? Well, metric tensor is going to allow me to now calculate the inner product, and once when I have the inner product, I can calculate distances and angles in the frame which is living on the surface, right? So I can actually calculate the distances of the properties of the vectors that are glued to the surface, right? So how I do this? Well, so a vector. So let's have a vector in here, right? So some kind of a vector A, call it capital A. So I'm going to have some kind of a vector A. Now this vector is gonna, so you can think of it in 2 ways, right? This is a little bit confusing in the beginning. You can think of it as a vector, just your regular vector sitting in R3, but you can also think it as this special vector which is living in the tangent plane onto the surface. So I'm going to consider it that way, and I'm going to write it this way, right? So which means, so this is alpha u EU plus B alpha V EB, right? So these are just the components of this vector computed in this basis. And I'm also going to have a B. And I'm using in here different indices. These are summation index. So this summation index is called the dummy index because nothing depends on it, right? So if I see in this, if I look into this expression in here, right? So the right-hand side only has alpha and beta because these are the free indices. The gamma cannot appear on the right-hand side because I summed over it, right? So I can now calculate my dot product between these 2 guys. Well, let's actually do this. So this is A alpha E alpha times B beta E beta, right? And again, this is the dot product in the outer space. So this is all linear, so I can take it out, right? So I'm going to have A alpha, B beta, then I have E alpha dot E beta, right? But this is just a definition of my metric tensor, right? So I have A alpha, B beta, G alpha beta, right? So I have double contraction. The result cannot depend on any of the indices because it's a scalar, right? But now what I can notice that I can use this contraction, so-called contraction, meaning summation of the pairs of indices with the metric tensor to produce a quantity which has a lower index, right? In the old notation, this is called a covariant vector. In the modern notation, this is called a form, but we are not going to go into this, right? And then I get a very convenient expression which says this. Right? But ultimately, if you want to calculate it, then you need to do this contraction in here. Is this clear? Good. So now I've equipped so now I am able to calculate distances, right? Meaning I can calculate the dot products. When I calculate dot products, I can do distances. And meaning I can calculate lengths, not distances. I can calculate lengths, I apologize, lengths, and I can also calculate angles. Okay, so when I have these two, this is really good, right? So this guy is very important, so it has a name. It's called the metric tensor, or sometimes it's called the first fundamental form. So why first fundamental form? Again, one would have to go into the theory of forms. Okay, good. So far so good, but that's not enough, meaning I haven't mentioned curvature yet anywhere. So the next thing which I want to do is I want to introduce the notion of curvature. And in order to do this, right, this is very convenient because I know where my surface lives. So what I can do is I can introduce the normal vector. So a normal vector n to a point, right? So the n is defined at every point on the surface. So I can actually put p in here to be precise, that I mean a particular point is defined as EU at that point P cross EV at that point P, right? Divided by the norm by the length of their cross product. This norm in here is your regular norm in R3, right? So this is just your x squared plus y squared plus z squared square root. So effectively what I do, I take these two vectors and I cross product them. And then I make a scared Hedgecock type of situation, right? So I assign to my surface, I assign kind of sticky needles that are sticking at the point. Right? For those of you who have done computer graphics, you have calculated this kind of before breakfast, right? Because that's the beginnings of the computer graphics in here, right? But that's where it all comes from. So this normalization in here allows me, so these guys are always have unit normal by construction, right? So at every point, n vector has a unit length. I made sure that this is true. And because I required in here that this U and EV are form a basis, this cross product is always non-zero, meaning I can always define a normal, right? I don't have some kind of pathological thing. So this is all very good. Right? Okay, so now, starting from there, I can actually define one more quantity. And now we are getting into domain of very interesting. Right? It's called a second fundamental form. So it's clear, right, that the E alpha dot n is equal to 0, right? And that's by definition. I've defined the normal vector to be the cross product of the two, so which means the dot product of this. So this guy n is orthogonal to the plane formed by EU and EV. So therefore, this has to be true, right? So if I take now derivative with respect to beta, and this is notation, by this notation, when I say d beta, I just mean derivative of whatever with respect to u beta in here, right? That's what I mean. So if I take the derivative of 0 is 0, surprise, surprise, right? And then I'm going to have a d beta of E alpha dot n, right? Now this is regular partial derivative, right? Which commutes with the dot product. This dot product is again in the embedding R3 space, right? So what I'm going to have in here d beta E alpha dot n, right? Plus E alpha dot d beta n, right? Okay. Which tells me that d beta E alpha dot n is minus E alpha dot beta n, right? Okay, so this is now just a mathematical mumbo jumbo, but we are getting to very interesting notions in here, right? So what I'm doing in here, so when I'm calculating derivative, so the derivative connects points in neighboring points. And you already feel if I'm in the flat space, right? So if I'm on the surface of if I'm on the surface of this board, right? So if I have a normal vectors, right, which are just doing which are just these guys, right? Something which is sticking out of the surface. If I move around, this normal vector doesn't change, right? And you would call this flat. But if I am sitting on this surface, right? And I take my normal vector, you see what happens to the normal vector as I move it, right? So the change of the normal vector from point to point is going to tell me something about the curvature of the surface that I'm working with.
So, are you planning to show, for instance, some of these for the paraboloid example?
The actual example?
Yeah.
No. Probably not, but I'm going to do what is called. Let me finish this, and I'm going to do one sketch. So then, okay, so we can, but we can do it. Man, it's not a problem, right? Okay, good. So is this abstract, too abstract, or should I actually do the actual calculation? I was thinking of doing it for. No, yes. Yep. Yep. Yes.
When you differentiate these two vectors at two different points, these two vectors, we are embedded in R3, but we are living on two different.
We're getting to a very, very important point, which is the next point. It's extremely important, right? So where the hell does this live? Right? And we're going to get to the notion of differential of covariant derivative very soon, right? Because so that's an excellent point. Right? Where does this thing live, right? And actually, this lives in R3. So yes, if I start with my tangent vector at point P, and if I differentiate it, I kind of slip off the surface, right? So I need to correct for this, and that's a notion of a covariant derivative, which is in the core of general T of relativity, right? Okay, good. So I'll do an example a little bit. So so now I'm going to introduce what is called the second fundamental form B alpha beta, which is, now let me just get the signs right. Right. So the convention is d alpha e beta dot n, right? But that's equal to minus e beta dot d alpha n, right? By this formula which we showed in here, right? So this is called a second fundamental form. It's rank 2 tensor with 2 lower indices, right? So it's not a curvature yet, but it's going to become curvature in a minute. So I'm going to define what is called the curvature tensor, right? And those of you who've done general TF relativity, don't scream at me. This is still not Riemann curvature. This is a kind of a baby version of the curvature, right? So I'm going to define a curvature tensor, which is now a 1-1 tensor. This is actually a matrix, right? Which I am just going to define as G alpha gamma, B gamma beta, right? I'm going to take this guy, multiply it with the inverse of the metric tensor, contract over the second index, meaning I contrast over first index. These are both completely symmetric, right? So these are symmetric forms, right? So I can swap these guys, and I get something called the curvature tensor. So this is now a matrix of 4 numbers, which is actually 3 numbers because it's a symmetric matrix, right? And now, as you know, any matrix 2 by 2 has 2 invariants. One of them is a trace, and the other one is the determinant. And these things have important names. So I'm going to define something called H, right? Which is just 1/2 trace of this tensor, which is in the fancy language of indices, written this way, because a repeated pair of indices, so I'm summing, right, sum of the diagonal elements, right? This is called mean curvature, right? And then something which I'm going to denote as K, some people denote it as G, but it's probably better to use K because G is used usually for something called Einstein tensor if you do general TF relativity, which is just a determinant of C, right? And this is called Gaussian curvature. So these are these 2 invariants. Now, since they're invariant, right, you can actually, now it's a little bit more story behind this, but kind of a little bit hand waving, right? So since this is a matrix, symmetric matrix, positive definite, right? I can diagonalize it. So if I diagonalize it, I'm going to get 2 eigenvectors. So these 2 eigenvectors are going to be orthogonal to each other, right? And they correspond to what is called 2 principal curvatures. So the maximum curvature and the minimum curvature. That's highly non-trivial statement which I've just made, right? And then the mean curvature is the mean value. That's why it's called mean curvature. Mean value of the 2 principal curvatures, right? Of the direction in which the curvature has a maximum and the direction in which curvature has a minimum, right? And the Gaussian curvature is a product of the 2. Right? So Gaussian curvature is gonna be very important. Because this is an intrinsic property of the surface, right? So in order to measure mean curvature, and these I'm just making these as statements. These require a lot of work to prove. The mean curvature. So mean curvature, you need to be aware of the embedding space. So you need to be aware that you have a 2-dimensional surface living in a 3-dimensional space to be able to measure this. Gaussian curvature, on the other hand, is an intrinsic property of the surface itself. Right? So you can prove that it only depends on the metric, and that is called the Gauss theorema egregium, right? Or the magnificent theorem. So Gauss was so fascinated when he discovered it that he called it the magnificent theorem, right? It's a magnificent result, right? So which means that the Gaussian curvature is something which you can measure from within the surface, right? So the fictitious living beings who are living in curved 2-dimensional space, who are not aware of their embedding, that they live in a flat 3-dimensional space, they would have no clue about this, but they would be able to measure this, right? And that's exactly what translates if you live in a 4-dimensional space-time, that you can actually measure the curvature of the space-time, right? So you can, from inside, we can measure it without referring to some kind of outside space. But anyway, so let's not go into this. So in the interest of time, right? So now let's actually get back to your question, right? So what are these guys, right? So let's actually calculate the derivative. So I take my tangent vector. So I take my tangent vector in here and I differentiate it with respect to this curve, right? So let's say that this was EU, right? And this is some kind of a U curve, right? So this is some kind of a gamma dot U, right? So this is the curve, which the kind of the coordinate curve of that So which means that I'm keeping V fixed along this curve. So now I take the derivative of that object, right? So in general, there is no reason that it's going to be tangent when I move further, right? Meaning, why would it be, right? There's no reason. Meaning, it's going to be some vector, right? But I'm going to use the fact that these two guys, right? So if I take EU, EV, and N, so these guys form a basis. So this is basis in R3, right? So which means I have two tangent vector and then I put one normal, and of course I've spanned the entire R3, right? So which means that I can write these guys, right, as a linear combination, right? So I can write them as a linear combination. I'm going to use capital gamma of the basis vectors, right, of the tangent vectors, right? Now I'm going to have two lower indices in here, right? And since I need gamma in here, I need to sum over gamma, right? So I have three indices. So I have an object which has three indices, one up and two down, which actually doesn't happen to be a tensor, right? But that anyways, right? Plus, and then I'm just going to write it down. I'm not going to prove it, that you can write it this way, right? That by this second fundamental term times n, right? So all of this is just a very fancy way of saying I have a vector and then I write it in terms of the components of some basis, where this particular basis is not any basis, but the basis which is formed by these three vectors, right? Okay? And this guy has a name, right? So this is called a Christoffel symbol of the second kind. So this is some kind of object which has three indices. So how can you calculate these objects? Well, I'm not, in the interest of time, right? I'm not gonna go through the gory details of the derivation, but what you essentially do, you just multiply the entire thing, let's say, by E delta in here, right? And then this term is automatically gonna go away because N is orthogonal to E, right? And then in here, you are gonna have something which looks like E beta dot E delta, right? And on the other side, you're gonna have something which is alpha beta gamma, and then you're gonna have E gamma dot E delta, right? Which is gonna give you G gamma delta, and then you can lower indices, and you can see you can see that you're gonna have something which looks alpha beta gamma, which is gonna be some kind of combination of alpha E beta dot E gamma, right? So it's a little bit more complicated, but it's just a sum of terms which look like this, right? Yes.
What is E gamma, E and E delta?
So these are the vectors, right? So these are the basis vectors. These are the same vectors, right? I'm just using these are exactly the same vectors. I'm just using different letter to denote them, right? Right? Because right, so you have some kind of a vector A, you can write it as AX EX, right, plus AY EY, right? And then for alpha and beta I use X and Y, right? And I'm just playing with indices, right? Because all I'm saying that this is a vector which I'm going to write as a linear combination of the two basis vectors, right? So these gammas are just the coefficients of that expansion. But these coefficients have three indices because that's where I started from, right? So all I'm doing is I'm just writing a vector as in components in a given basis. That's all. And these are exactly the same vectors. So alpha, beta, gamma is 1 and 2. Okay, so that gives me what is called the Christoffel symbols of the first kind, and then I can make the second kind guys by multiplying them with the appropriately placed metric tensors. Okay? And then as a punchline of all of this, I actually want to introduce a very important notion. Right? So I'm going to introduce a notion of a covariant derivative. So covariant derivative is just going to be a fancy word of taking your regular derivative and then chopping off everything which is sticking out of the surface after I take the derivative. So I'm going to denote it, but there are different people denote it differently. I'm going to use a nub line here. Some people use a capital D. So I am going to introduce a covariant derivative, let's say, with respect to E alpha of E beta, which is just gamma right? So this is a covariant derivative for a basis vector. It just tells me what happens to the basis vector when I move it along the surface. And all I do is I chop off the part which is sticking out of the surface. Right? So I'm guaranteed that this guy is going to live in the tangent vector next door, in the tangent place next door. So do it. And now you can generalize this idea to an arbitrary vector. And let me see where I want to write it, maybe here. So I can calculate this. So let's have two vectors A and B, right? So all of them are, so they live in the tangent space, so the tangent vectors to the surface. And I can ask what is the covariant derivative in the direction of A of a vector B. Yes?
You did not chop off. You kept the term with the opposite sign. So you still have a term in the normal direction.
No, I erased I removed the.
But if you compare with what you still have a contribution from N, right?
Yes. I'm sorry. I was too quick in there. Sorry, my bad. No. Sorry, you're absolutely right. Meaning this is nonsense what I wrote. I apologize. So this is d alpha e beta. No, it's good, right? Yeah. Sorry. Thank you. Yeah. Sorry. This was complete nonsense, right? So you take the actual derivative. And then you chop off the normal thing. Right? That's what happens when I rush things, right? Okay. So let me just write the final expression, right? As for completeness. So the final expression is going to look something like this. A alpha d alpha b gamma plus gamma alpha beta gamma A alpha b gamma e gamma, right? And very often in the literature, you're going to see expressions that are written something like this, right? B gamma. So essentially, this means I am taking the derivative of a tangent vector B in the direction of tangent vector A, and this mumbo jumbo in here essentially allows me to get a tangent vector which is tangent to the nearby plane. And this is now closely related to something which is called a parallel transport, but that's beyond the scope of what we are talking in here. Okay, good. Hopefully I didn't make any more mistakes. Okay, good. So, any questions about this so far? So now let's actually go a little bit. Let's actually do an example, right, which is going to be important for doing numerics on these objects. Yes.
Is there a reason why you're taking all your manifolds to be simply connected? Because you're embedding them in space. So I'm guessing you can, like, the entire formalism will still be valid for, like, say, a torus, right?
Torus is embedded.
Yes, but it's not simply connected.
Torus is not simply connected. I'm assuming in here that the domain D is simply connected. So the parameter space of a torus is simply connected because this is 0, 0 to pi, 0 to cross 0 to pi. So the surface itself doesn't have to have a simple topology, but I'm assuming that the domain of the parameter space has a simple topology. Right? Okay, good. So now, actually, let's try to take let's make things a little bit less abstract and take what is called the Monge representation, or Monge gauge. So this is essentially a or elementary calculus representation of the surfaces. So this is the one where I assume that my U1 is just X and that my U2 is just Y, right? And that my surface now can be written as R is equal R of X and Y, and it has components in here X, Y, and some kind of a function of X and Y, where this function is not differentiable and so on and so on. So that's example of paraboloid, right? So now we can do the example better, right? So for example, X squared plus Y squared, that would be a surface like this. X, Y, Z, right? And then for a given X and Y, so for a given pair X and Y, there is a point on the surface where this in here, this height in here, is f of X and Y, right? So the height function. So now, what I can do is I can use my machinery, and now I am gonna. So now be careful. This little X. This is not X of the embed. So this is not this guy, right? This is not this guy. This is the tangent to the surface at point X and Y, right? So this is just gonna be dr dx. This is just gonna be a vector. So if I take a derivative with respect to x, I get the 1. Right? If I take this derivative with respect to x, I get 0. Right? And if I take a derivative with respect to x, I get the derivative of x. Right? And then if I write this as ey, ey dy, then I get 0, 1 dyf, right? And now if you do this for a paraboloid, so for a paraboloid, ex would be 1, 0, and then what would be this 2x, right? And then ey would be 0, 1, 2y, right? And you already see that these guys are not, they're not orthogonal to each other, right? And they are not unit length, right? So for example, we can now construct the components of the so we can construct the metric tensor. So this is going to be EX, right? So this is going to be EX dot EX, EX dot EY, EX dot EY. They commute, I can do this, right? Times EY. So this metric tensor is going to look like, so if I multiply this guy with myself, I'm going to get 1 plus dxf squared, right? If I multiply these two guys together, so these two components are orthogonal, and I'm going to get in here dxf dyf, right? I'm going to get dxf dyf in here, and then this guy with itself is going to be 1 plus dyf, right? So that's going to be my metric tensor, right? So now I can, in terms of the so for the paraboloid, this guy is then going to be, so help me out in here. So it's going to be 1 plus 4x squared, right? Then this guy is going to be 4 times xy, 4 times xy, and then it's going to be 1 plus 4y squared, something like this. So that's what's going to be, that's what it's going to look like. And as you can see, further away you go, these vectors become longer and longer. Now I can do the whole mumbo jumbo with the matrix inverses, which I'm not going to do because it's a pain. You would have to calculate the determinant. It's in the notes. But what I'm going to do is I am going to write the expression for the second fundamental form, which is reasonably straightforward, which is 1 over root, and I'm going to have in here 1 plus dxf squared plus dyf squared, right? So that's a kind of older brother of the curvature tensor, or a cousin of the curvature tensor. I'm writing it because second derivatives pop up, and this is really important that these second derivatives pop up. And then I'm going to have in here dx dyf. In here I'm going to have a dx dyf, and in here I'm going to have a second derivative, right, with respect to x. So this is the second fundamental form. So why I'm so excited that I see second derivatives, right? Because you remember from elementary calculus, what does the second derivative tell you about the function? Just a regular one-dimensional calculus. Curvature, exactly, right? It tells you how the curve is, what is the curvature of your function, right? So you take the first derivative, you find if the zeros of the first derivative tell you if this is a minimum, maximum, or the inflection point, and the second derivative tells you it's curving up or down, right? So this is all just a more sophisticated version of a one-dimensional calculus. So it's really not surprising that these second derivatives are popping up. So from here, you can calculate the curvature tensor, which is a lengthy expression, meaning completely straightforward, but Mathematica does it in a second, right? And then from these guys, you can actually derive the mean curvature and the Gaussian curvature. Right? And now I am going to write, I'm not going to write the expressions for mean and Gaussian curvature in their whole glory, because there are 3 rather nasty terms, but I'm going to write them in the limit where these derivatives are small, right? So I'm going to assume that this is slightly undulated surface. So you have something which is more or less flat, and then you undulate it a little bit, right? So kind of, it's a very nice day, and then you're by the lake, and there is a little bit of breeze. So meaning it's not too wavy, but it's a little bit kind of undulating. So in this case, the mean curvature becomes the Laplacian of f, right? So this is just a Laplacian. And then we have in here approximately equal, right? So all of this mumbo jumbo for this simple triangle in here. And this is incredibly important for numerics. So ultimately, you want to do something, meaning this is all beautiful, but not much you can do analytically, because as you've already noticed, even for a simple object as this one, these guys become quite nasty, right? Ultimately, what you want to do is you want to find a way to discretize these things and to kind of put them on a computer. And this particular formula in here is going to be incredibly important, right? Because it tells me that the Laplacian of my surface, right, is intimately related to the mean curvature of the surface, right? And this is again not surprising because the Laplacian is the second derivative, right? So these are these guys, so it's a sum of these guys. And these guys are actually incidentally very easy to discretize. Okay. Any questions? Yep.
How are you able to measure the Gaussian curvature without knowing the metric of the space? Do you have a...
No, you know the metric. You know the metric, but
You know the metric.
Something which you can calculate from inside, right?
Oh, okay.
So the metric, effectively, so what you do is you can measure angles of a triangle, right? And then, long story short, in a flat space, what you learned in elementary school is that the angles of the triangle add up to 180, right? If you put a triangle on the surface of a sphere, you realize that this is not the case, that sum is larger. And if you get something like negative curvature, it's less than. So you can measure triangle, you can construct triangles, and you can measure angles, and that tells you something about the metric. That gives you the Gaussian curvature, right? Yeah, through the derivatives of metric. Okay, good. So now let me actually talk about physics. I was hoping that the mathematics part is going to be shorter, but anyways. And how to implement these things in a computer simulation, right? So how to do these things. Essentially the idea is going to be that we are going to write a energy which depends on the curvature, and this energy is going to depend on the mean curvature. And the justification for that is, as I said, because this thin structure is very thin, then the bending degrees of freedom are the most common ones. Okay. Hopefully this is going to be dry enough. So Helfrich, a German physicist, like 1975, 1976, thereabout, I might be off by a few years, wrote a beautiful paper where he analyzed the bending energy of a liquid, of a bilayer, of a lipid bilayer, right? And then he just said that the energy of this object is an integral over the area. So this is the area element of the surface. I'm going to use 2. Some people use 1/2. So some kind of bending modulus, meaning how much energy does it cost me to make a bend, h minus a naught squared, right, plus something called kappa g Gaussian curvature. So he derived this, but kind of in a hand-waving, really physics way. Right? So that the energy of the low energy fluctuations of a membrane object can be written in this way, right? So H is the mean curvature, which we spend a lot of time discussing, and K is the Gaussian curvature, and what is H naught? H naught is what he called the preferred curvature, right? Because you can imagine making your bilayer out of two types of lipids where they have different preferred curvature, so you have something which wants to be curved without costing you any energy. I'm going to assume that this is equal 0 in what I'm going to do, because that makes my life easier for the purposes of this tutorial, right? And then if you want to find the configuration of your membrane, you need to minimize this energy in terms of the position vector, in terms of u and v, and u and v are entering in this H in this complicated mumbo jumbo, right? So you take a variational calculus, you take the variational derivatives with respect to u and v of this thing, you do something like this, and then you get a complicated set of partial differential equations, which you pull your hair out in order to solve. I mean, you can solve them in certain special cases, right? What I'm going to assume, I'm going to take a different approach. I'm going to solve this numerically, right? So what I'm going to do is I'm going to take my membrane, which is up there, and I'm going to discretize it. And then I'm going to tell you how to do this on a computer. It's still very complicated, meaning technically, right? But conceptually, it's not that bad. I'm also going to assume that kappa is a constant, right? And that kappa g is a constant. So these guys in actual lipid membranes, so lipid bilayer membranes, which you can make in a lab, or something which resembles the cell membrane. So these are of the order of, let's say, 10 to 20 kT. So it's sufficiently high in energy, it's not going to fall apart thermally, but it's sufficiently low that it can actually fluctuate. These guys are much less is known about these guys. This is called the Gaussian splay modulus. This is tells you how much it costs you to form things like saddles. But I'm not going to care about this guy, because if these guys are constants, right, then I can write my energy. I can write it as 2 kappa integral ds. And I said I'm also going to assume that H naught is equal to 0. This is just assumption to make my life easier. Right? H squared, right? Plus kappa g little g integral over the surface of the Gaussian curvature, right? So these are integrals, these are definite integrals, they are of the area of the entire surface, right? So why I don't care about this guy? Because there is something called Gauss-Bonnet theorem, which tells me that as long as I am not changing the topology of my surface, so as long as I am just kind of undulating it, I'm kind of massaging it, but I'm not poking any holes or creating new boundary, this thing is a constant. This is a topological invariant. And since it's a constant, doesn't really contribute to the energy, right? So I can drop it. So as long as I'm not changing the topology of my surface, meaning as long as I'm not poking holes in my vesicle, right? I can completely drop this guy. Right? And I can end up with the deceptively simple expression. Now, this is nasty, right? Because this is the surface integral over a curved surface, right? So this ds hides a lot of things inside. So it hides the square roots of metric tensor in here, of the determinant of the metric tensor, right? And this guy is a nonlinear function of the coordinates of the surface, right? So if I actually want to disentangle this into a set of equations that I want to solve, right? Even if I want to find a configuration, if I want to minimize this expression in here, I have to do this in terms of the coordinates, and I have to choose the coordinate representation. I'm going to get set of nested differential equations. But in general, what I can do is I can approximate my surface. I can take my surface, my membrane, and in here I'm cheating a little bit because I'm having a surface with a boundary. And if I have a surface with a boundary, then this Gauss-Bonnet theorem becomes a little bit trickier because you have to worry about what's happening. You have to worry about what's called the Gaussian curvature of the geodesic curvature of the boundary. But let's for a moment imagine that this is my rendering of a sphere. Okay, so this is a sphere. So what I'm going to do is I'm going to represent this. I'm going to approximate it as a bunch of triangles. And now I can keep on drawing this until cows come home, right? But I'm going to approximate this as some kind of triangulation. So I have a bunch of points that are connected with edges. These edges form triangles, and these triangles meet at 5, 6, 7 of them meet at the vertex. I've discretized my surface. There is, meaning this is a dot, right? Meaning, so people do PhDs in terms of how to do this, how to properly discretize a manifold, right? But that's the idea. So now I have a system of a finite number of particles. So I went from an infinity dimensional system from a functional, right? From something which depends on the continuously on the coordinates, right? To something which is discrete, which is multidimensional, but which is discrete. And then in principle, I can now write an equation of motion for each of my vertices. So now Ri is in some reference frame. So let's say this is the position of the vertex I. Right? So I can now write the equation of motion, some kind of a friction coefficient times the velocity. I always write it in overdamp limit because these things are living in fluids and they move very slowly. Right? So I can write it as a force balance, Aristotelian physics, right? So the force, the velocity is proportional to force, is minus dE dRi, right? And I'm going to put a twiddle on E because now this E in here is the approximate version of these guys, of this guy, right? So I want to approximate this thing on a surface. Okay? So sorry, I want to approximate this guy on something which is triangulated. And this immediately begs the question: so how am I gonna approximate something like a mean curvature on a triangulated surface? And that's a very complicated problem also, which has some elegant solutions which mathematicians frown upon, and it has some more accurate solutions which are bloody complicated to implement. So you always have to find a balance. But let me sketch the idea. So what you do is, I show it in the notes. You can actually show using relatively straightforward algebra. It's quite tedious, but you can show that this expression which is in the box in here, so this expression which is in the box in here can be written as 1/2 kappa now, an integral over the surface ds, which is the metric of, meaning the area element of the surface, metric tensor, inverse of the metric tensor, this is far from obvious, right? But if you're interested, I gave the derivation in the notes. So you can actually express this Hamiltonian, or this free energy, as a dot product of the derivatives of the normal, right? And this is really not, if you stop and think about this, is really not that surprising, because it just tells you, because the change of the normal, derivative of the normal tells you something about the curvature. So if I want to construct a scalar out of two vectors, I need to somehow dot product them, right? So that's the idea. But then what can you do? You can be David Nelson and say like, well, okay, but this to me looks like spin physics, right? I like the X-Y model. So what I'm going to do is I'm going to discretize, I'm going to write my effective free energy with some renormalized kappa in here. And this kappa meaning one, we can discuss what the normalization is, as sum of all pairs of triangles, right? Do something like this. So how is this related to this? Well, very easy, because Ni minus Nj squared, right? This is just Ni minus Nj dot Ni minus Nj, right? And then these are all unit length vectors. So Ni dot Ni is going to give me 1. Nj dot Nj is going to give me another one. And then I'm going to have 2 times Ni dot Nj, right? Okay. So I'm going to have 2 times 1 minus Ni dot Nj. I really don't care about 1. This is just an overall, because if I sum over all the triangles, I'm just going to have something which is proportional to the area, which I don't care about, right? And then I'm going to have the X-Y model, right? Ni times Nj. But you know probably from your condensed matter classes that this is the continuum limit of the X-Y model, right? So if you take this guy, and you can write this as Ni, so you can write as Nj is Ni of R plus delta R, and then you take the mumbo jumbo of the Taylor expansion, you're going to get that the leading term is just this. Right? So it's very conveying expression. Yes?
Does the size of the triangle
absolutely
play any role?
Absolutely, it does play. Yes. No, absolutely. Right? I'm kind of swiping all of these things under the rug, right? And that's actually the downfall of this approach, right? Because these are the convergent property. And then now, do I need to go over this, or is this clear? I'm assuming that everybody has taken basic condensed matter course, which essentially explains you how to take the continuum limit of the X-Y model. So effectively, what we have now, we have a bunch of kind of a hedgehog, of kind of angry hedgehog, like the one with the kind of spiky, the more of a like sea urchin, right, of a surface, right? So with all the tiny normals that are sticking out everywhere, and then if you want to calculate the curvature of these things, we can. So if you want to calculate not the curvature, if you want to calculate the bending energy, which is associated with that configuration, what we need to do, we sum over all the edges. We take, for each edge, we take the 2 neighboring triangles. We calculate the dot product of the two triangles. If they are parallel, we are happy. If they are pointing slightly off, if there is a splay between them, we add this up, and we get the energy. And then one can do some sort of Monte Carlo approach, where you randomly displace your vertices, calculate what is the cost of this move, and then reject or accept according to Metropolis rules in order to get the configuration. So this approach is going to allow you to find the minimum surfaces, the surfaces that are minimizing this this energy in here, or they can allow you to do thermodynamics, to do the kind of thermal averages, like for example, you want to calculate the normal correlation functions and stuff like that using Metropolis Monte Carlo. You can do more than this because these ends, right? So these ends for every triangulation, for every triangle, this is not really a triangle. For every triangle, I can calculate the normal by taking the cross product of the two vectors that form this guy. Right? So this normal vector is in some funny way gonna depend on the positions of my vertices of my mesh. So I can take the derivatives of this expression or of this expression in terms of the positions of the vertices, and I can get forces on those vertices. These are nasty expressions. I mean, it's completely straightforward. These are nasty length expressions involve a lot of vector calculus. We give them inside the papers. If anybody's interested, I can give you some references. Right? And then you can build a molecular dynamics or Langevin dynamics type of code, which would then allow you to do the dynamics of these objects, right? By calculating the forces on each of these vertices, and then integrating the equations of motion, which then brings you to the 21st century because nothing prevents me to add active forces on the vertex, for example. I can even be more ambitious. I can actually add activities on the coefficients or areas, and now I've built a theory or the framework which allows me to study how membranes can grow or how they can shrink and things like that, right? So I can start studying non-equilibrium dynamics of the membrane objects. The disadvantage of all of this is that this is actually quite a bit of mumbo-jumbo mathematics, and you're talking about the order of 10,000 lines of C++ code to get this implemented, in full glory. So how does this connect to the vertex model? It connects to the vertex model because these meshes are usually, or when I do them, they're represented using the half-edge data structure. Exactly the same thing which I was mumbling about on Monday, right? So if you really want to implement them on a computer, you implement this. There are many ways you can do this, but one of the, in my opinion, most elegant ways is using this type of mesh half-edge data structures, which then allow you to very quickly walk over the mesh and kind of find who the neighbors are. And it also allows you to do one more thing, which is incredibly important, and that's to flip edges. So why would you want to flip edges? If you flip edges, that's how you emulate the fact that the membrane is a fluid, that membrane can actually flow. This is far from obvious. That was worked out by Gomper and Kroll in the mid-90s, in the series of papers, from 1991 to maybe early 2000s. So the idea is you introduce the fluidity in these objects, the fact that these things don't sustain shear, that they can actually flow, by allowing for something like this to happen. So you have a configuration like this, which goes to a configuration like this. You flip the bond. I'm now making this as a statement. I'm really not proving that this introduces fluidity, but if you're interested, Gomper and Kroll were two guys who actually worked this out in gore details and showed how this worked. So, and in the last few minutes, let me tie this to the Laplacians, because you mentioned there is actually this is all very elegant, and this is very nice because this maps you to the XY physics, and then statistical physics community is very happy because we know a lot about XY model, right? Because you can do all the RG and stuff like that. The problem is, early on, people noticed that there are numerical issues with this approach, and one of them is that for example, you take a unit sphere, which you know that has to have a constant energy, and you just increase the number of triangles, make triangles smaller, add more and more, the thing doesn't converge. In practice, it really doesn't matter unless you're a mathematician, right? But people came up with more sophisticated schemes, and the more sophisticated schemes are based on using the fact that this is indeed a Laplacian. So what you do instead is you approximate the Laplacian directly, right? And I'm going to write this formula because you might encounter it from time to time, because this actually appears sometimes in finite element codes. And this is so-called a cotangent formula. So the idea is simple, is instead of kind of doing this kind of physics which has to do this kind of mapping to the XY model, or sort of mapping to the XY model, you work directly with the Laplacian, and then you notice that you can write an approximate, a very good approximation of a Laplacian of a function. So let's say I want to calculate a Laplacian of a function f, which is defined on some kind of mesh. Right? So I want to calculate, so this is my I, these are j, k, l, right? So I want to calculate the Laplacian of a function which is defined on these discrete points of a mesh which looks like this. So one can show that the mean curvature, that's again found in Gomper and Kroll, the original derivation goes back to 1960s, probably like Brezovsky or guys like the string theory guys. So they were the first guys to start thinking about these things. So 1 over sigma I, I'm going to tell you in a second what this is, and I. J, right? And then this becomes, what you do is, so first, so this is the normal vector onto the vertex. Now you can ask what on earth is the normal vector onto the vertex, how I do define this? Well, I define it by taking the average of the normal vectors on the triangles that share that vertex. Lij is the length of this edge, and what on earth are sigmas? The sigmas are what is called a dual area. So what you do, you construct a dual. It's a very interesting theory of this. So every lattice is going to have its dual lattice. And then these guys in here are sigma ij. So these are length of these lines. And then sigma I is just the area of a dual cell. And now finally, how does one calculate sigma ij? So sigma ij is Lij over 2, and then cotangent alpha ij plus cotangent beta ij, where this in here is alpha ij and this in here is beta ij. So you take the edge, you take the two angles that are facing that edge, take their cotangent, multiply them by the length of the edge divided by 2, and you get the edge in here. It's highly non-trivial, meaning it's not hard to prove. Right? Why am I showing this? Because this is very relatively straightforward to implement, doesn't have the problem with convergence, and it works really beautifully, right? Meaning it's really kind of in a practice, really very elegant way to do this. And I'm showing it because this formula appears quite often in several different regions of physics. especially when you're doing stuff like finite elements, very often because this is a diffusion operator, right? So this is diffusion operator. So if you want to study diffusion on the curved space or diffusion on any lattice, you're going to have to be able to calculate just a second, you have to calculate the Laplacian, and this is the way to do it. Yes, Yuan.
You showed us in the Monge representation that the Laplacian can be approximated as the mean curvature. And here you've given us a formula for the mean curvature. But generally, it has some more complex relationship to the Laplacian.
Well, this is very more generally, right? But what you need to do is you need to introduce what is called Laplace-Beltrami operator, right? So I would need to kind of construct a Laplacian from covariant derivatives, and then I get a nested thing which has the square roots of curvature and of metric tensor and so on, right? So this was a more kind of a hand-wavy argument to show you that these things are related to each other. But in general, curvatures are related to Laplacians, right? And it's really not that surprising because the curvature is the second derivative and Laplace is second derivative, so it's not that. Okay, I think I'm going to stop here. I hope that this gives you kind of a general idea how these things are done. There are codes out there. Surface Evolver is absolutely fabulous code. Unfortunately, it was written in 1980s in C, so it's impenetrable. But it's the code if you want to deal with the source code. I'm going to shamelessly advertise something which we have with my former postdoc and now collaborator Daniel Matos Fernandez, something called Pi Membrane. If you Google that, there is something called the Tri-Membrane by a group in Germany, and so on and so on. So there are actually quite a few codes out there if you're interested in how all of this works before you get your hands dirty and start implementing it yourself. And thank you very much.